Hi, welcome to the last lesson of Chapter 7, 7.5, Properties of Trapezoids and Kites. Now, to prepare for today's lesson, what I need you to do is I need you to grab a half sheet of paper and cut it in half again and place it right on page 215. So go ahead and do that. Pause the video and then restart whenever you're ready. On the next page, page 216, you're going to grab the other half that you had left over, and you're going to put it right on page 216. Now, we are going to do two proofs there. There's a lot of proofs in this chapter if you haven't noticed. In the next page, you're going to write down where the problems are going to go. So the first one is right here, number 1, number 2, and number 3. Now let's look at some of the theorems that we're going to look at. We're not going to be able to prove all of them, but we are going to be able to prove a few. So here you have the following. It's called the isosceles trapezoid base angle theorem. And we're going to talk about what exactly is a trapezoid in just a bit. Okay. So if a trapezoid is an isosceles trapezoid, then each pair of base angles is congruent. Meaning this is congruent to this, and this is congruent to this. Okay, and we are actually going to do the proof for this one in one of the pages. So the converse of that is if a trapezoid has a pair of congruent base angles, then it's going to be an isosceles trapezoid. So we're actually going to be proving this one and not this one. Okay. Next page. All right, the next one is the isosceles trapezoid diagonal theorem. It says a trapezoid is isosceles if and only if its diagonals are congruent. So if this is an isosceles trapezoid, then the diagonals are going to be congruent. The next one, the trapezoid mid-segment theorem, states that the mid-segment of a trapezoid is parallel to each base and its length is 1/2 the sum of the lengths of the bases. Okay. In other words, this plus this, okay, divided by 2 gives you mn. Okay. Now we're not going to go ahead and prove that, but just know that the sum of AB and DC divided by 2 is going to equal 2 mn. Now, a kite, and we're going to define these polygons in just a bit. If a quadrilateral is a kite, then its diagonals are perpendicular. If a quadrilateral is a kite, then exactly one pair of opposite angles are congruent. And we're going to actually join these two, and we're going to prove these two in the same one, in the same proof. All right. So let's talk about what exactly is a kite, what exactly is a trapezoid. So let's do that on page 215. Now, a trapezoid is a quadrilateral that has one pair of sides that are parallel and one pair of sides that are not parallel. Okay, so as you can see here, these are parallel and these are not parallel. All right, so that's basically what a trapezoid is. It's a quadrilateral that has one pair of sides that are parallel and one pair that are not parallel. If it so happens that the non-parallel sides are congruent, then that's called an isosceles trapezoid, which is the one that we're going to be dealing with today. Okay, so if I have a trapezoid, okay, if I have an isosceles trapezoid, we're going to call this trapezoid A, B, C, and D. Okay, so since this is a trapezoid, this side here is parallel, the other two are not. Now, the theorem that we're going to prove says that if this is an isosceles trapezoid, then the base angles are congruent. Okay, so given okay, that this trapezoid has the following segments congruent. AD congruent to BC. Okay, making this an isosceles trapezoid. Okay, so if this is an isosceles trapezoid, then the base angles are going to be congruent. So we have to prove that angle A is congruent to angle B and angle D is congruent to angle C. So we're going to do a really nice trick here. Here's what we're going to do. I am going to construct a segment creating a parallelogram between these two, D, C, and A. So I'm going to create a line and I'm going to make it parallel to AD. So I'm going to make this one here parallel to this one here. And I'm going to call this point right there E. By definition, this is going to be a parallelogram. Okay? Now, because it is a parallelogram, we know that the opposite side is going to be congruent. That means that EC is going to be congruent to AD. Okay? So because these two lines are parallel and AB acts as a transversal, angle A is going to be congruent to angle CEB by the corresponding angle theorem. Now, if you look at triangle CEB, it's isosceles. The base angle theorem tells you that angle CEB and angle B are congruent because it's isosceles. So by the transitive property, angle A is going to be congruent to angle B. And now we just need to figure out angle D and angle C, but we're going to do that a little bit towards the end. Let's go ahead and begin our proof. All right. Okay, first step is AD is congruent to BC. That is given. Okay, the second thing, we constructed EC parallel to AD. Okay, it's my auxiliary line. Okay, and I made it like that. And yes, you can do that. Okay, so therefore, by definition, okay, AECD is a parallelogram. Definition of a parallelogram. All right, so it's a parallelogram. So what does that mean? Well, because it's a parallelogram, now you're going to have, let me see, AD congruent to EC. Okay, and it's because of the parallelogram opposite side theorem. Okay. All right. So then the next thing is you have angle A congruent to angle CEB. Why? Because of the corresponding angle theorem. And I keep forgetting to name these. Corresponding angle theorem. Now, if you look at that triangle, angle CEB is going to be congruent to angle B. Why? Because this is an isosceles triangle. Okay, so by the base angle theorem, those are going to be congruent. And therefore, by transitive property, angle A is going to be congruent to angle B. Transitive property. So now the only thing that's left is showing that angle D and angle C are congruent. So here's how we're going to do this. Because this is indeed a trapezoid, these two here are parallel. Okay, which means that makes angle A, okay, supplementary to angle D. And angle B supplementary to angle C. And that's because of the consecutive interior angle theorem. Oh, can't see it. Consecutive interior angle theorem. So here's the thing. We already know that A and B are congruent. So when you have two angles that are supplementary to the same angle, they're going to be congruent, which makes angle D congruent to angle C. And that's called the congruent supplement theorem. Now, do I expect you guys to come up with this whole proof all by yourself? No, I really don't. Okay? I do expect you to understand it and know where it came from. So one of the things that, because I've been throwing out all these words and I haven't even defined them, so I apologize for that. Okay, so these right here, let me just talk about these. These sides right here, they're called bases. Okay, these right here, they're called base angles. Okay, those and those. Okay, so those are called base angles. And these non-parallel sides are called legs. See, even evolution, gets into math. Triangles evolutionized and got legs. That's a joke. All right, let's look at the next theorem. So the next theorem is on page 216. And we're going to do two theorems at once. Okay, so here you have a kite. A kite is basically a quadrilateral that has two pairs of sides, congruent, but they're not opposite. Okay, they're actually adjacent to each other. And what we want to do is we want to prove two things on this one. Okay, so given that A, B, C, D is a kite. It's an actual shape. I'm spelling kite wrong. Kite. Not a speller, guys. Okay, we need to prove that angle B is going to be congruent to angle C and that BC is perpendicular to AD. So for this, we need a diagonal. We have to. Okay? So we know that this side right here is congruent to itself. Therefore, the triangles are congruent by side, 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 making angle B and angle C congruent by CPCTC. So boom, that takes care of the first one easily. So let's do that. All right, 1. A, B, C, D is a kite. That's given. So what does that mean? Well, the definition of that is that AB is going to be congruent to AC and BD congruent to CD. Definition of a kite. Okay, definition of a kite. So by the reflexive property, AD is congruent to AD. Reflexive property of congruence. That makes those two triangles congruent. Triangle ABD congruent to triangle ACD. Why? The side-side-side congruence theorem. Therefore, by CPCTC, angle B is congruent to angle C. CPCTC. Easy. All right. So then the next thing we got to prove is that BC is perpendicular to AD. So here's what I want you guys to think about. Okay. D is equidistant to both of these endpoints. Therefore, D lies on the perpendicular bisector of BC. Okay. And so does A. A lies on the perpendicular bisector of BC. So that means that A and D are going to just have to be perpendicular. They have no other way. Okay, so D is on the bisector of BC. Okay, D is on the bisector. Now it's one of those theorems that we talk about. Is the converse of the perpendicular bisector theorem, and I'm not numbering these right. So it's the converse of the perpendicular bisector theorem. This came from, I believe, chapter 1. Yes, no, chapter 1, chapter 6. Okay, lesson 6.1. It actually came from there. So therefore, BC has to be perpendicular to AD. Definition of perpendicular lines. Oh, can't see it. I get, guys, when I'm doing these, I'm like looking at the paper and I'm not looking at my screen to see if I'm even showing it. So I apologize for that. So make sure you pause the video so you can actually finish writing these down. And sorry about the numbering today. It's the 5th video I do today, so my voice is tired. And I'm tired. And I'm hungry. And it's a Saturday. All right. So let's go ahead and do the examples. All right, so let's look at the first example. Okay, so it says, show that ORST is a trapezoid, then decide whether it is isosceles or not. Okay, so first things first, let's check to see if it's a trapezoid. So in order to check to see if this is a trapezoid, I have to check and see if RS is parallel to OT, okay? And I have to check that RO is not parallel to ST. That's how I check to see if it's a trapezoid or not. So what do I need to do? I need to find the slopes, okay? So let's look at the slopes. The slope of RS. Now, since it's graphed for me already, I can just do a simple rise over run, no problem. So RS, that's 1 over 2. The slope is 1/2. The slope of OT, that is 2 over 4. Okay, so that does equal 1/2. So far, so good. The slope of RO, okay, RO is a vertical line. So that means that it has an undefined slope. And the slope of ST is, let me see, 2 over 2, which is and negative, so that's -1. Okay, so the slopes happen to be different, which is what we want. So is this a trapezoid? Yes, it is a trapezoid. Okay, so yes, it is a trapezoid. How do I know if it's isosceles or not? Well, here's the thing. The non-parallel sides would have to be congruent. Okay, so let's look at the distance of RO. RO is vertical, so I can just count. 1, 2, 3. Okay, so RO is 3. But I can't do the same thing with ST. I actually have to do the distance formula. So for ST, okay, I have to do the distance formula. So the differences of the x's, that's 2 minus 4 square. Differences of the y's, 4 minus 2 square. That's going to be -2 square. 2 squared, that's going to give me 4 plus 4, which is going to be the square root of 8. Now, here's the thing. I don't even need to solve for it. I know that these two are not the same. They're not equal. Therefore, they're not congruent. So, therefore, this is not an isosceles trapezoid. It's just a regular trapezoid. So Yes, it is a trapezoid. No, it is not an isosceles trapezoid. So that is example number 1. Let's take a look at the next example. Okay, in this next example, let me zoom in a little bit. It says the stone above the arch in the diagram is an isosceles trapezoid. Find the measure of Q, M, and J. So here's the thing. The base angles are congruent. So I know this is kind of hard to see, but you have basically a trapezoid. Okay, they tell you that these are congruent. You have K, L, M, and J. Okay, this is 85 degrees, and this is parallel to this. So remember, the base angles are congruent. So that means that this is also 85 degrees. To figure out what J and M is, keep in mind that they're both congruent, and L and M are also consecutive interior and supplementary. So to find the measure of angle M, you have to do 180 minus 85. Okay, so that's going to be 95. So the measure of angle M is going to be 95. And it's also going to be the one for J. All right. So here you have your solutions. And of course, measure of angle K, 85. Very, very simple. You just got to remember that the base angles are congruent here. And the consecutive interior angles, or the consecutive angles in a trapezoid, are supplementary. So that's example 2. Let's look at example number 3. In the diagram, MN is the mid-segment. The mid-segment is the segment joining both midpoints on opposite sides of the trapezoid. So one of the things that we did remember is that MN is 1/2 of the sum of the bases. So PQ and SR. So nice thing is we actually know both of these. So MN equals 1/2 of 12 plus 28. Okay, so then that's going to be 40, which is going to end up giving you 20. So MN is going to be 20. Simple as that. And that, ladies and gentlemen, is example number 3. Just remember, this plus this divided by 2 gives you that one. Example 5. Find the measure of angle D. Now remember that these two angles right here are going to be congruent. Okay, so we're going to call that X and X. The sum of the angles, the sum of the angles in the quadrilateral is going to be 360. So X plus X, that's 2X plus 115 plus 73 is going to equal 360. So now it's just a matter of solving this. So 115 plus 73 equals 188. That's 2x plus 188 equals 360. So subtract that from the 360. You get 2x equal to 172 divided by 2, and you get x is equal to 86. So therefore, the measure of angle D is 86. As simple as that. Let's take a look at the last one. Okay, what is the most specific name for the quadrilateral? Looking at this quadrilateral, the only thing that you can see here is that the diagonals bisect each other. And that's it. So the only thing that we can say here is that A, B, C, D is a parallelogram. And that's it. That's all we know. We cannot deduct that this is even a rhombus either, because we don't know what this angle here is. Okay, I mean, we could, if we were to say that's vertical and that's vertical, these two are congruent, but that's not enough to say that, that they're going to be at right angles. So that is all we know. So this is the last example for lesson 7.5. Please make sure you have taken all the notes. And thank you for joining us, and make sure to subscribe.